5 grams of oxygen gas is reacted with 4 grams of hydrogen gas. Which reactant limits the reaction? First step we said is write out the chemical equation. So 5 grams of oxygen gas is reacted with 4 grams hydrogen gas. And so I know right off the bat that this is going to be one where I have O2 plus H2. Nope, not H2O. I don't know what I'm thinking there. That's not even remotely right. Just H2. So O2 plus H2. These are the two things I have reacting, and they are going to make something. And so to do this, you're going to go ahead and get out your predicting reaction product sheet, and by doing that, you say O2 plus H2. That is going to be compound plus compound. Oh, sorry, it's element plus element. My bad. Element plus element is only a synthesis reaction, so it's going to make a oxygen and hydrogen together, and oxygen and hydrogen put together make this wonderful substance known as water. And so we now have to balance this guy. And so we have 2 oxygens, 1 oxygen here, so we put a 2 right here. That gives us 4 hydrogens on this side, so we have to put a 2 right here. So first step, write out and balance the equation. Next step, what you're going to do is you're going to say, okay, let's pick one of the 2 to start with. I'm just going to say let's start with the first one, 5 grams of oxygen gas. What you're going to do is you're going to convert from the unit of the first one, which is grams of oxygen gas. In the 5 grams of oxygen gas, you're going to convert into the units of the second one, which is grams of hydrogen gas. And so we're going to go from 5 grams oxygen gas, and we're going to go into grams of hydrogen gas. And we're going to see if it's bigger or smaller than 4. And so let's set this up. So we start off with 5 grams oxygen gas. So 5 grams of oxygen gas. Set up our table. First step is always go from grams oxygen gas into moles of oxygen gas. Okay, and so to do this, we're going to have to look up the atomic mass of oxygen. Well, oxygen is 16. If there are 2 of them, it's just 32. So 32 grams oxygen gas in 1 mole. That should be a 1, and 1 mole O2. So once we've got that, that nicely cancels out grams oxygen gas. Those are gone. We're at moles oxygen gas. Next step is always to go ahead and convert from what we started with, moles of what we start, to moles of what we want. We said here that we're going to convert to grams of hydrogen gas. And so we want to go to moles of H2. And so we have to look up here. We say H2 has what coefficient? Has a 2. O2 has what coefficient? Has a 1. So this is a 2 to 1 mole ratio. So that goes ahead and cancels out our moles of oxygen right here. And so let's us continue here. We're looking for grams, we said, of hydrogen gas. So let's continue it farther. We want to cancel moles of H2. We want to go to grams of H2. And so to do this, we once again want to look up what the molecular mass is of H2. Hydrogen is 1.01 is its mass for one of them. So 2 of them would make 2.02. And so that then cancels out our last one. And let's take a look. So, oops, didn't mean to cancel the 2 there. So that cancels moles H2. We just have grams H2 left. So if you get your calculators and multiply across, we say 5 grams times 1 times 2 times 2.02 on top, then divided by what's on bottom, divided by 32, divided by 1, divided by 1. And so when I do this, I get 0.63125. And so 0.63125. And so to the right number of significant figures, this would just be 0.6. Now, let's take a look. Of these 2 guys right here, I have 0.6 grams of hydrogen gas that I need to use up all of my oxygen, every last bit of it. How much hydrogen gas do I have available? I have 4 grams. So if I only need 0.6, I've got 4 available. Do I run out of hydrogen gas? The answer is no. That means hydrogen gas has some left over. Hydrogen gas is in excess. If hydrogen gas is in excess, that means my limiting reagent is oxygen. And so this is my final answer. Oxygen gas must be my limiting reagent because of the fact that the hydrogen has a whole lot left over whenever it's done. We only needed 0.6. We have 4 available. So that's how you figure out which one's a limiting reagent. Let's work out a second one. So what we're told here is we have 14.3 moles of sulfuric acid is reacted with 15.1 moles of sodium tartrate, which is the limiting reagent. First step, write and balance the chemical equation. And so to do this, we say we have sulfuric acid. It's an acid, so we know it starts with hydrogen. And sulfuric is going to be the ic acid means 8 on the end, so sulfate. So SO4. SO4 sulfate has a valence, if you look on your on your polyatomic ion sheet of -2. Hydrogen, on the other hand, has a valence of +1, so we need 2 of those, so H2SO4. And then it's reacted with sodium tartrate. And so we're going to add that to sodium tartrate. So sodium Na. Tartrate is probably not one you remember off the top of your head, so you look on the polyatomic ion sheet again, and you see that tartrate is C4H4O6. So C4H4O6. Sodium, if you look on your periodic table, has a valence of +1. Tartrate on the periodic table has a valence of -2. So it's Na2C4H4O6. Well, looking at what type of reaction this is, we say that we've got a compound plus a compound. Compound plus compound is almost always going to be double displacement from your predicting reaction product sheet. And so that means that the anions switch places. So we start off with H, which is our first cation over on the left side from the sulfuric acid, plus the tartrate from the other one. So HC4H4O6, like that. Now, hydrogen is +1. We said tartrate was -2, so H2, C4H4O6 to form tartaric acid. And then plus our next one, which is we start with the sodium, Na, and then plus our cation or anion for the first one, which is sulfate, SO4. Sulfate we said was -2, sodium is +1, so Na2SO4. And so this is what we've got for that. Now we've got to balance our particular guy here. So we're looking at things. We have 2 hydrogens on the left, 2 hydrogens on the right. Excellent. We have 1 sulfate on the left, 1 sulfate on the right. Excellent. We have 1 tartrate on the left and 1 tartrate on the right. Excellent. So this turns out it just balances already. Sometimes that happens. So we have a 1-to-1-to-1-to-1 mole ratio for everything. And so setting this up, we would start off with one of the two that we start with. We can either use the 14.3 mole sulfuric acid, or we can start with the 15.1 mole sodium tartrate. I'm just going to pick the first one because I figure, why not? So 14.3 moles of sulfuric acid. So we start off with this. First step is always go to moles of what you start with. We already got moles of what we start with, so we don't have to worry about that. We can just go from moles of what we start with, moles of H2SO4, to moles of what we want. Remember, you always want to convert from what you start with to the units of the other one. The units of the other one here are going to be moles of sodium tartrate. And so we want to go to moles of what we want, which is sodium tartrate. And so sodium tartrate, we said, was Na2C4H4O6. And so what's the mole ratio? 1-to-1. Woo! So this is a very simple one. We get 14.3 moles of sodium tartrate. Na2C4H4O6. All right, just like that. So we look at this. We have 14.3 moles that we use up of the sodium tartrate. We have 15.1 moles available to sodium tartrate. That means that there is extra sodium tartrate left over. The sodium tartrate is in excess. Therefore, since the sodium tartrate is in excess, the limiting reagent must be the sulfuric acid. So sulfuric acid here is our limiting reagent. And so that is how you find limiting reagents. So that being said, what about our next step? What if we actually have a problem like this where we had to figure out other things, not just which one's the limiting one, but figure out like what products are made, how much of them. So let's take a look at how we do that. So once you found the limiting reagent, what you want to do is you want to solve the stoichiometric calculation using the limiting reagent only. So you do it just like we did before, but you simply use the amount of the limiting reagent. So if all the reactant masses are given, you thus must add a step to your stoichiometric calculation, a step to the ones that we did before. First step we talked about here is we said you want to determine the products of the reaction. That's the first step. Second step, write and balance the chemical equation, same as it was before. Third step has now changed. Third step is now determine which reactant is the limiting one, is the limiting reagent. Once you've found the limiting one, you get to step 4. Convert from the limiting reagent, the amount of the limiting reagent amount, to the wanted amount using factor dimensional analysis, using our table the same way we have before. And so you'll use the mole ratio, of course, that you figured out over in question 2, same as we have before. So let's go ahead and let's try out something like this to see if this will work out. So Equal amounts of iron 2 nitrate and potassium hydroxide, that's at 14 grams each, are reacted. What mass of potassium nitrate is produced? First step, find the products. So we have iron 2 nitrate and potassium hydroxide are reacted. So we know we're going to react these two. So we say iron 2 nitrate. So we have iron, we have nitrate. A quick look at the polyatomic ion sheet tells us that nitrate is NO3. So we have NO3. Now it's iron 2, so it has a charge of +2. Nitrate has a charge of -1. And so we'll have this guy right here. And so we're going to take this and we're going to react it with potassium hydroxide. Potassium is K. Hydroxide is OH, like this. Now potassium, if you look on your periodic table, is +1. Hydroxide on your polyatomic ion sheet is -1. So those are already balanced. Okay. Then this reaction is we have a compound plus a compound. If you look at your prediction reaction product sheet, you say compound plus compound is double displacement. So we're going to start off with our iron, and we're going to put it with the hydroxide, the anion of the second one. And since iron is +2, because it's iron 2, and hydroxide is -1, we need 2 of those. And I'm running out of room again. So we'll say plus our next one, which is potassium, is our cation, plus the anion is nitrate, NO3. Potassium is +1, nitrate's -1, so those are cool. No problem there. To balance, we look and we say, okay, we've got 1 iron on the left, we have 1 iron on the right. That works. We have 2 nitrates on the left and only 1 on the right, so let's put a 2 over here. But to put the 2 there, that changes 2 potassiums on the right, so I have to put a 2 right here to get these to balance. But that gives me 2 hydroxides on the left, and oh, good job, we have 2 hydroxides on the right. So those sort of work out here. So this is what we start with. Next step is let's figure out which one's going to limit. We know we have 14 grams of iron 2 nitrate and 14 grams of potassium hydroxide. Doesn't matter which one we start with. Let's say we're going to use the iron 2 nitrate. Let's say we start with that one. And so let's start with the iron 2 nitrate, 14 grams. So I have 14 grams of iron 2, whoops, FeNO3, that's not right. Whoop, put a little parentheses there, ignore that. NO32. So this is what I start with. First step is I want to go from grams of what I start with, FeNO32, to moles of FeNO32. Okay, to do this, I'm going to have to find the molecular mass of iron 2 nitrate. And so I know here I have 1 iron. I look at the periodic table, tells you that iron is 55.85 plus 2 nitrogens, so plus 2 times the mass of nitrogen, which is 14.01, plus 6 oxygens. 3 times 2 is 6 oxygens, so 6 times the mass of oxygen, which is 16. And so doing that, you get 179.87. So 179.87 is what we get for that. That's in 1 mole. And so starting off with that, that nicely cancels out our grams of iron 2 nitrate. And then so that's going to take us to the next step. Next step is going to be to go from moles, what we start with, which is the iron 2 nitrate, to moles of what we want. What we want is the other guy. And so we start off with iron 2 nitrate. We're looking then for the potassium hydroxide. And so we want to go to moles of potassium hydroxide. KOH. A lot simpler to write. So we now need to find what are the coefficients here. Potassium hydroxide, coefficient is 2. Iron 2 nitrate, coefficient, nothing out there, so it's just a 1. And so this is what we have here. From there, once again, we want to cancel out our units. Moles of the iron compound are gone. That means we can go to our next step. We can continue this out. We can go from moles of potassium hydroxide to going to be grams of potassium hydroxide. And so once again, we get out our periodic tables, and we say that potassium is 39.10, and we're going to add that to 1 oxygen, which is 16, plus 1 hydrogen, which is 1.01, so we get 56.11 grams of potassium hydroxide. And so doing that cancels out our last remaining unwanted unit, the moles of potassium hydroxide. That's in 1 mole there. And so from this, once again, we can multiply it out. We say 14 grams of iron 2 nitrate times 1 times 2 times 56.1, and we're going to take that and divide it by what's on bottom, 179.87, and then divided by 1. And so when you do this, then we get a final answer of 8.734 to two significant figures would be 8.7 grams of potassium hydroxide. So let's take a look. Is that we need to use up all of the iron 2 nitrate, we need 8.7 grams potassium hydroxide. We have how much potassium hydroxide available? 14 grams. So that means there's extra potassium hydroxide available. The potassium hydroxide is in excess, so therefore the limiting reagent must be the iron 2 nitrate. So we have found our limiting reagent. Yay! And so now that we've got that guy right there, we're going to use him to figure out the answer to the problem, which is what mass of potassium nitrate is produced. And so to do this, we're going to start off, we said, with 14 grams of iron 2 nitrate. So we say 14 grams FeNO3, same as we did before. We're going to convert from grams FeNO3 to moles of FeNO3, because your first step is always go to from grams of what you start with to, or always go to moles of what you start with. And so here we actually already figured out this step. We figured out it was 179.87. One of the nice things about this system is that you do sometimes figure out some of the steps already. You've already got them done. But this time, instead of going from moles of iron 2 nitrate, to potassium hydroxide, we're looking here for potassium nitrate. And so we're going to go to moles of potassium nitrate, KNO3. Now here we say KNO3, we look for it up here, KNO3 is right there, has a coefficient of 2, so the mole ratio will be 2 to 1 again, so 2 to 1 ratio. And so that gets us here. The question was what mass, so we're looking for grams of that KNO3. And so we want to go from moles of KNO3 to grams of KNO3. And so get out your calculator and your periodic table again. And so we have potassium, which we said was 39.10. So we have one of those plus 1 nitrogen, which is 14.01, plus 3 oxygens, so plus 3 times 16, the mass of oxygen, gives us 101.11. And so 101.11 is our mass here. That's in 1 mole. Setting this up is that, taking a look at this, we have canceled the grams of the iron nitrate. We've now canceled the moles of the iron nitrate. We've canceled moles of potassium nitrate. We have only grams of potassium nitrate left. And so simply by taking out the old calculator, we say 14 times 1 times 2 times 101.11, multiplying across the top, divided by the bottom, 179.87, and then divided by 1, divided by 1. And so doing that, we end up, when you work this out, getting 15.7395 to two significant figures. That'll be just 16. And so the answer is 16 grams of potassium nitrate are produced. That would be our final answer there. So this is how you go about setting up a full-scale problem whenever you don't know which one's a limiting reagent. And so it is possible to get that final mass here, but it does take a few steps. So we got that there. Let's take a look at another one. Okay, a sample of propane of mass 44.1 grams is burned in 34.7 grams of oxygen. How many moles of water are released? And so to set this up, our first step, as we said, is to write out the chemical equation. So we have propane, and I did not mention what propane was, is that propane is C3H8. Should have mentioned that. I forgot to put that in the problem. So propane C3H8. And if I were actually giving this to you, I would tell you what the mass is. And if not, tell me and I'll tell you what it is, or what the formula is, because that's not one that you're supposed to know just yet. So we have C3H8. This is what we're going to take, and we are going to combine this. It says is burned in oxygen. So the propane and the oxygen are what we start with. And so we've got these two. Keyword here, burned. It's on fire. If it's on fire, that means it must be combustion. If it's combustion, then we know it forms oxides with both elements, as you know from your predicting reaction products sheet. And so that should be an arrow, not a plus sign. No arrow, plus sign here. And so we're going to get the carbon oxide, CO2, plus the hydrogen oxide, otherwise known as water. And so we got this one right here. So to go ahead and balance this out, we have 3 carbons on the left, so we need 3 carbons on the right. We have 8 hydrogens on the left, which would mean that we would need 8 on the right. So what times 2 is 8? 4. So we have 4 right here. And so with our oxygens, we have in the carbon dioxide, we have 2 times 3 or 6 oxygens there, plus 4 more in the water. So 6 plus 4 is 10. So we need 10 oxygens on the left. And so we put a 5 right there. And so C3H8 plus 5O2 yields 3CO2 plus 4H2O. That's what we get for our chemical formula. Now, we're told we know the amount of propane, 44.1 grams. And we know the amount of oxygen, 34.7 grams. We don't know which one limits. We've got to figure that out first. And so this is what we're going to do to start things off. Let's go ahead and we say, let's pick one to start with. I always like the first one, so I'm going to start with the first one again, is that we have 44.1 grams of butane. And so we start off 44.1 grams of butane, which is C3H8. Okay? First step, always go from grams of what you start with to moles of what you start with. You always want to go to moles of what you start with first. H8. Okay, so to do this, we want to find the molecular mass of the propane, C3H8. And so we have 3 carbons, so 3 times 12.01, the mass of carbon. Plus, we have 8 hydrogens, so 8 times 1.01 is 8.08. And in doing that, we get 44.11. 44.11 grams of C3H8. And so that goes to moles of this. Next step is we want to go from moles of what we start with, C3H8, to moles of what we want. And in this case, what we want is the other guy, which is oxygen. We want to find what this one is. So moles of oxygen, oxygen's O2. So let's look at what we have here. The oxygen, coefficient's 5. Propane, coefficient's 1. So we have a 1 right here. And so from this right here, we've got moles of oxygen now. We have canceled so far. We've got most everything canceled. We've got the grams of propane canceled. We have moles of propane canceled. We're to moles of oxygen. But we're given the number of grams of oxygen, so we have one more step. We're going to have to go from moles of oxygen to grams of oxygen. Oxygen is 16 for the mass of one of them, so 2 of them would be 32. 32.00. And so that's in 1 mole here. And so that cancels out our last step. That cancels out moles of oxygen right there. Now at this point, our last step is quite simply just to solve this. And so when you do that, you take the ones on top, 44.1 times 1 times 5 times 32, divided by the mass of, on the bottom, so that's 44.11 divided by 1 divided by 1. And so when I get this, I get 159.96 to 3 significant figures would be simply 160 is what we have here. So to burn up 44.1 grams of propane, I need 160 of oxygen. Do I have 160 of oxygen? Absolutely not. I don't have 160 of oxygen. And so since I don't have enough oxygen for this to work, the limiting reagent must be oxygen. And so that means that when I set up this next one, I'm going to start with 34.7 grams of oxygen because it's the limiting reagent. So let's set that up. We start off 34.7 grams of O2. First step is to go from grams of what you start with to moles of what you start with. So go to moles of what you start with first. And so 1 mole, oxygen we said before was 32. We already figured that out. Next step, we want to go from moles of what we start with to moles of what we want. What does this question ask for? It said how many moles of water are released. And so we have our water right up here. And so we're going to moles of water, H2O. And so water, we have what number in front? We have a 4. Oxygen, we have what number in front? We have a 5. This is one of those weird uncommon ratios, a 4 to 5 ratio. And so we've got that. We now want to go from moles of water to what we're looking for. It says how many, oh, actually we're done. Never mind. So completely get rid of that last step because it asks you simply how many moles of water. Sometimes you'll have that happen where you really don't need that last step. And so if you don't need the last step, I mean, why do it? So at this point, let's just multiply it out. We have 34.7 grams of oxygen times 1 times 4 divided by 32 on the bottom divided by 5. And so when we do that, we find that we get a final answer here. I get unrounded of 0.8675. Since we started off with 3 significant figures, our answer will be rounded 3 significant figures, so 0.868 moles of H2O. And so that would be our final answer.